Right, so last lesson you looked at some collisions. To be very specific, we looked at elastic collision. So that's one particular type of collision. And you have done two scenarios, wrote a CR, and found that the total amount of momentum before and after a collision would be the same. And we call this idea and concept the conservation of momentum. And the definition for this is that in a closed system, which means energy is enclosed within the system and it doesn't leave the system, the total amount of momentum before and after an event would be the same. And when we say event in physics, we mean it could be collisions or explosions. So if we were to represent this using a mathematical equation, we would write this. The P is a lowercase p and represents momentum. And then there's a little subscript called T, which stands for total. So momentum total and momentum total. And there is a little apostrophe thingy, but we do call this pi in physics. And it's an indication that is a different version to the one on the other side of the equation. For example, from a different time, before or after an event. So here are different ways that you can write the equation. If you don't want to use the little pi thingy, you could, again, add more subscript to after the T and say before and after, or you can call it initial and final. All right, so both of these, well, there are three ways of writing it, using pi, using before and after, or using initial and final for representing total momentum. So when we look at the types of collision, the one that we looked at was elastic collision. And the definition for that is the elastic collision is where you do not have a net loss in kinetic energy in the system as a result of collision. So you can notice that the velocity is there. The velocity is never lost. You still have things traveling. Maybe it's a different speed, but then it's evenly distributed between the two vehicles that was traveling. And we would say that we have conserved kinetic energy in elastic collision as well. So we could represent this using this mathematical equation, and that's an elaboration from this. So total momentum, or you can say momentum of car number one and momentum of car number two, would be equal to car number one and car number two after collision. Now, if you were to use m times v, which equals momentum, you can actually elaborate and expand the equation a little bit further. So I'll let you pause the video and think about how you would do that, and then you can continue on. Okay, this is how you do it. Momentum one, you can expand it to mass of one and mass velocity of object one plus mass of object two and velocity of object two would be equal to mass of object one and velocity of object one after collision, mass of object two, velocity of object two after collision. So this basically is your P1. So momentum of object one before collision. This is your momentum of object two before collision. Momentum object one after, momentum object two after. And so again, you can write it slightly different. Instead of using the pi, you could use initial or final. That's totally up to you. Now let's do some practice questions. In your notes, you have two questions and they look like this. There is one rule about velocity though. When an object is traveling east or north, which means towards the right-hand side or upwards on a diagram, then the velocity for that object would have a positive number. If it's traveling south or traveling downwards, then it will have a negative number. All right, so for example, if something's traveling 10 meters per second north, then it would be positive, but if it's 10 meters per second south, it will be negative 10 instead. So pause the question, and I want you to attempt question 1 and 2. All right, assume that you have finished it. So this is how I would represent it visually. And the momentum of the bumper car before collision would be this, if you had done the math correctly. And then the total momentum of the blue and the red bumper car before collision would be 400. And after collision, it will also be 400. And we did not calculate this because we don't have all the numbers, but we know this based on the conservation of momentum. We're going to assume that this collision happened in a closed system where nothing is being lost. Okay, so the velocity of the blue bumper car after collision is our unknown. So we kind of assigned blue car as object number 1. So this is velocity of object 1 after collision, v1f. That's the only unknown in here. All the other things I would have subbed in the number and calculated through these steps. So you can pause and have a think about it. And on the left-hand side, basically, if you really don't know how to solve questions that look too complicated, follow the step, read the problem, draw diagrams, determine which is your unknown, write out the equation, and then sub in everything except for the unknown and rearrange things, solve your equation, and then you can do a reality check, which means you can sub in the value 30 meters per second back into the velocity, and then have a look at the left-hand side and the right-hand side to see if the momentum before and after the collision is equal. All right. So based on this logic, I'm going to ask you to check over your question 2 by yourself and then cross-check it with your partner. Okay, let's move on to inelastic collision in this lesson. So on Schoology, you would have your lesson 4, I believe, being posted as inelastic equation, momentum and inelastic equation. So again, I want you to do 2 simulations using exactly the same link that I've given you last lesson. And this time we're going to click this button called inelastic collision. All right, it's no longer elastic. Now, something about this inelastic collision is if you click it and I click run, you will notice something very strange. The car will be stuck together and they will travel together being stuck. So let me change the velocity value and show you that one more time. All right, this is what inelastic collision is. It's usually represented that the car are kind of glued together, and then there will be some loss in kinetic energy. So follow the instruction in this, set the values according to these numbers here, and then do your data analysis. And we'll look at the momentum before and after collision, and you'll draw some conclusions on that. All right. Once you have completed both your scenario number 1 and scenario number 2, I want you to do this bit. Compare and contrast the total momentum before and after collision for both of the scenarios. See if there's any different. And then I also want you to compare before and after velocity. Now this one, I want you to think back to your elastic and inelastic collision velocity. Do you notice something that is different? All right. Now we would define elastic collision as no loss in kinetic energy. However, if we look at inelastic collision, back in this question, you would probably have realized that although the total momentum before and after collision does not change, there seems to be a slower velocity happening if the collision is inelastic. So you can see that there is a loss in total kinetic energy, but no loss in total momentum. And that is a major, major difference between the two types of collision. All right, so in one very simple term, the total momentum is conserved. However, kinetic energy is not. Now, if we were to represent things using a mathematical equation, just like last time, we'll use P before and after equals to each other. And then if we expand it out a little bit, it would be mass and velocity of object 1 equals to mass times velocity of object 2 would be the momentum before. And then there is something special about the after this time. Because object 1 and object 2 are kind of glued to each other after the collision and they move together. And that is the reason why we would actually treat mass 1 and mass 2 as one bulk object. So you need to add them together before you times it by the velocity, because there are no two separate velocity anymore. The two objects are traveling together, so there's only one velocity. So this inside the bracket is the two masses combined after collision. So this entire thing on this side would be the momentum after collision. And that is the equation for inelastic collision. Okay, so that's it for this lesson. And next lesson, we'll do some practice questions for you guys to try and work out inelastic and elastic problems.